want to kind of run through some of the basics about transformations with matrices. What we started with in this example, we started with just a single set of 3 points, right? And you can see that right here. I started off, and we're going to run through each of these transformations. We're going to kind of describe what the colors are and what those individual things mean. You can see here, I drew a picture of a triangle, A, B, and C, right? This black triangle. This is the original, what we call a pre-image, right? And from this image, or this pre-image, I can get the coordinates from my particular triangle and label them like this, A, B, and C. So the coordinates X and Y are showing up here. One of the easiest transformations we can do is called a translation. A translation is simply moving the triangle, moving the matrix, whatever it happens to be, left, right, up, or down, right? That is how we define a translation. It is one of the transformations that we talk about. In this example, we're going to take our black triangle here, and we're going to move it right 3 and down 4. Okay, this is pretty basic. This is really nothing complicated. You're going to be adding and subtracting essentially, right? One of the first things we're going to do is I need to create what we call the coordinate matrix. Okay, this matrix consists of a 2-row matrix by a certain number of columns. Okay, the columns will be determined by how many points you have in the original image. In this case, we have a triangle, so we have 3 different points. In some instances, you may only have the coordinates written down. Some you may have the picture, just like you see in the worksheet that we have. Here, I've written it down. Point A is the point 1, negative 1. You can see that right here. So you're going to over to the one right for X and down 1 for Y. For B, we did 3, 2. You can see that one here. And then 4, negative 2. So we're going to go over 4 and down 2 to find C. And this is the original matrix, all right? When I grade your assessments, one of the first things I'm going to look for is, did you have the original coordinate matrix written down properly? The next thing is we need to take the transformations that are going to be happening. This is right 3 and down 4. Remember that going to the right is a positive number, going up is positive, and going down is negative, just like going left is also negative. So here we have a positive direction and a negative direction, okay? So what's going to happen is we're going to add a transformation matrix. This matrix for a translation is just literally which number am I going to be adding to the X coordinates? That's going to go here. And what number are we going to be adding to the Y coordinates? That's going to go at the bottom here. They'll always be the same, right? Each of these 3 numbers have to be the same, just like these 3 numbers have to be the same, right? So we would add 1 plus 3, 3 plus 3, 4 plus 3, negative 1 plus negative 4, 2 plus negative 4, negative 2 plus negative 4. What that will do, that will give us what we would call our image, our final result, right? 4, negative 5, 6, negative 2, and 7, negative 6. We can see that transformation happen in the image, or the graph. The black is the original, the pre-image, and then we have the red, denoted by prime. The transformation has happened, and this is called the image. And so we would have right 3, so we're going to go right 3, and then we're going to go down 4, right? So, and that's translations. There's nothing confusing about that. There's nothing I can make more complicated about that. I can just simply tell you to move it left, right, up, or down, so many values, and you would create that matrix that looks like this one, and you would just kind of create that. I would look, if I'm looking for grading papers, I'm looking for pieces and parts and partial credit, I would expect to see something like this. You don't need all the words here or even the labels, but you do need to have the original coordinate matrix, the transformation matrix, and then the final image matrix written out as an equation. And that's it. The next thing I would want to talk about, which is relatively just as easy, would be what we call a dilation. This is kind of magnification. We're going to be kind of making it grow in size or shrink in size. And here again, not really complicated. And in fact, the entire problem is just right here. I want to take that triangle and I want to dilate it by a factor of 2. In other words, I want to make it twice as big. Well, that's more on that in just a minute. I want to magnify each side length of this triangle to make it twice as long, right? So I've just basically, by multiplying 2, it's a scalar product, right? We're going to take 2 times 1, 2 times 3, 2 times 4, 2 times negative 1, 2 times 2, and 2 times negative 2 to get this image made. So this is my pre-image. We're multiplying by scalar, and that can be a whole number, it can be a fraction, it can be a decimal, it can be anything, right? In terms of graphing on a coordinate plane, it's nice to have whole numbers or half numbers. Other than that, it gets really awkward, and I probably wouldn't give you that to graph, maybe for just numbers if you didn't have to graph it. But then this is what my image turns out to be. And you can see that blue triangle up top. This blue triangle represents that dilation. You can see here that this triangle exists as half the size of this one. Let me be more specific. This side length is half of this one, or the blue side length, A prime to B prime, is going to be twice as long as the one here. Now, if you notice very quickly, if you think about it, this little triangle is definitely not half the size of this gigantic triangle. In fact, this triangle is 1/4 the size. If I look at the area of the triangle, which is what we tend to focus on, the space inside the triangle, there are 4 black triangles inside this big blue triangle. Now, mine is not drawn perfectly to scale, but if you drew this on a piece of graph paper, you would absolutely see that you could fit 4 of these black triangles inside here. Side length scale by the factor you multiplied by, in this case it's 2, but area will do that by 2 squared. Not that you need to know all that, but when I do a problem, I like it to make sense. This triangle and this triangle don't look like they're halved, right? And so that's how it works. And that's dilations, right? That's relatively nice. It's easy, not anything to worry about, but those are the 2 easy ones. Translations and dilations are super simple. I want to kind of go over the next 2, but first I want to introduce these to you and get you to write them down. Okay, we have here reflections and rotations. There are 4 reflections that we typically deal with, and there are 3 rotations. We have the x-axis reflection, the y-axis, the line y equals x, and the line y equals negative x. Each of these matrices is what you need to know in order to do the reflection or the rotation. Notice here, this matrix will rotate an object 90 degrees counterclockwise, or, I should erase that, well, no, or negative 270 degrees clockwise. And so I have to be very careful. Sometimes I'm going to give you directions that are saying, say clockwise, sometimes it'll say counterclockwise. You have to be very careful about those kinds of things and note what's happening, okay? This should have a negative on it, right there. I would have these written down, refer to them as you're doing these problems. You're going to use matrix multiplication to choose whichever matrix is appropriate and multiply times your coordinate matrix, right? So let's do a reflection first, and we'll come back and do a rotation. A reflection looks like this. I took the original coordinate matrix, the one we've been working with, and I just wrote it down right here. It says reflect over the y-axis. So I chose the y-axis reflection matrix, and then we're going to multiply across here and down here to get these numbers, right? So negative 1 times positive 1, let me write this down. Negative 1 times positive 1 plus 0 times negative 1. Let me point this out. Negative 1 times positive 1, that goes right here. And then we're going to go to the next number, 0 times negative 1. Remember, you go across this one, but down this one. And this number that we just calculated, this is going to give us negative 1, right? So that's just gone, and you have negative 1 at the top. This number is what we put right there. Okay, and I'm going to follow this pattern. This is just matrix multiplication. If you remember how to do this, if you need to go check that out, there's an entire video dedicated to that. We're going to go again, this row, and then go down like this. It's going to be negative 1 times 3, so it's negative 3 plus 0. Then you got negative 1 times 4, that's negative 4, plus 0. It's nice because I know the second number isn't going to have any impact because it's multiplying times 0. So it's really just the first number that I'm multiplying by. The second one, I'm going to go to the second row here, so I'm going to go to the second row on this one. I'm going to do 0 times 1, which is 0, plus negative 1 times 1 again. So I get negative 1. 0 times 3, plus 1 times 2 here. 0 times 4, plus 1 times negative 2, which is negative 2. And this gives me that image right here. My pre-image is this one. This is the reflection matrix. I did the multiplication, which for the most part, you can do in your head once you get the pattern down. Take time with that. It's important that you get that pretty easily. Okay. Now, if I go back up here, we reflected over the y-axis. Okay. The y-axis is the vertical axis. We can see the y-axis right here. We reflected just over that axis, and you can see the green triangle represents the reflection in the y-axis. I drew those points from my matrix, and I just graphed them, and it looks like a mirror image. Okay, give or take my issue with scale factors here, almost all good. Okay, the last thing we're going to do is a rotation. Okay, this is a rotation of 90 degrees clockwise, and so we chose we chose 90 degrees clockwise, which would be here. That's actually true. I should erase these negative signs. Okay, the negative signs aren't necessary because we're describing that negative direction by saying clockwise and counterclockwise. All right, so remember, just so we all sure about this, clockwise is a positive rotation, or counterclockwise is a positive rotation, and clockwise is going to go just like a clock hand would around, and that's a negative direction. So what we have here is a angle measure that is 90 degrees counter or clockwise, and I'm going to choose that angle here. We're going to set the problem up essentially like we're going to do that matrix multiplication just like we did before. And here I have my original matrix, and now I'm going to bring down that rotation matrix for 90 degrees clockwise, right? That's like a negative 90 degrees, just to show you, right? 90 degrees clockwise is this bottom matrix right here. All right, we're going to take this matrix, we're going to multiply that times our coordinate matrix. One thing to note, if you haven't paid attention, every time I've written this matrix down, it's been out front or on the left side of this matrix, right? That is the only way this happens. Now, if you had a 2-point object like a line segment and you're trying to reflect that, this would be a 2x2 matrix. And technically, you could put this on either side. But let's be consistent. Keep the transformation matrix on the left side of the object. And then you can multiply through, and that's always going to work that way. You won't ever have to worry about having something else go wrong or get something backwards. You can always do it this way, okay? And so what you're going to do is you're going to multiply through just like before. I'm not going to take the time to do that because we did that before. You multiply through, take careful and be consistent about your multiplying. Remember to go across in the first, down in the second. You're going to get this matrix, okay? And if we kind of plot that matrix on our little graph up here, you can see this is a rotation kind of in this direction, down 90 degrees. You can see the black matrix. If I rotate that 90 degrees, I'm going to get this picture, okay, the pink one. I would be very, very careful about rotations and trying to do this by hand. Rotations are the one thing that sometimes it's very awkward to try and get. It's not just something I can just kind of map over to the other side of some line, or if I can just move it a certain space. These transformations, matrices, allow you to do all of these points all at the same time in one mathematical operation. That way we can keep things organized, and it's basically just addition and subtraction with some basic multiplication with ones and negative ones and zeros. So the computation isn't super complicated, but that's essentially the entire lesson in a nutshell. Hopefully that made sense. Try those. One thing I did want to do is on the worksheet, if you got the worksheet that I gave out in class, there is no rotation matrices on it. I somehow got the ones confused. What I'd like for you to do is, if you did get the one that I gave out today, maybe you're absent and you're watching the video at a later date, what I'd like for you to do is to take For question 15 and 16, which there aren't 15 and 16, it's just numbers up to 14, right? But for 15, I'd like you to take number 11 and rotate it 90 degrees counterclockwise. Okay, rotate number 12 180 degrees counterclockwise, and we can call these numbers 15 and 16. Hopefully that made sense. If you have any questions about this, please let me know and send me a message, and I'll get back to you as soon as I can.